Good afternoon, all. So, welcome to CS Katha Barta. Today, it's a pleasure to introduce Dr. Jibesh Patra. So, he is an assistant professor in the Computer Science and Engineering Department at IIT Kharagpur, and his research interest focuses on the applications of large language models in software engineering and software security. He earned his PhD from University of Stuttgart, Germany, and where he worked on analyzing code corpus to enhance the correctness and reliability of programs. Welcome, Dr. Jibesh. Please go ahead. Yes.
Yeah, so thanks, Subankar, for the nice introduction. Yes, just before I start, I wanted to tell that please feel free to interrupt me if you have any questions in the middle. Mm, yeah, and I want this talk to be a bit interactive if it's possible. So, yeah, let me start with that. Uh, I guess it's still going through, right? Subankar, can anybody just say yes?
Yes, yes.
Perfect. Yeah. So I think the introduction are done, but still I want to reiterate. So I am here in Kharagpur since last year, around May 2024. I joined as an assistant professor, and you can find more information about me on my personal website. And primarily, my research interest, as rightly pointed out, is on software engineering, applications of AI on SE, in large language models for SE, software security, and also programming languages. So let me start by talking about two terms that are typically discussed in the software engineering community in general. So one is AI for SE and SE for AI. So AI for SE is about using AI to enhance software engineering tasks. So I think many of us are develop software regularly, and AI for SE is primarily about using AI for those kind of tasks, and SE for AI is just a kind of reverse, where you use software engineering techniques and principles to build a robust AI system. So I wanted to start with this just to make the clear that this talk is primarily about AI for SE. So I'll start with a brief introduction of what are the current trends. So how developers use LLMs in their development tasks, and later I'll show an application of one such task in software engineering domain. So the current popular applications for AI, like in particular LLMs in this domain, are I think for code generation we have GitHub Copilot. For bug finding we have Deep Code. So for automated testing we have Test Team. Similarly, for even code documentation and modernization, so there is a tool called Sweep. So these are all new tools that have come up in the very recent years. They primarily use AI for solving various software engineering problems. And about the usage of AI for software development, there is a lot of predictions. So you have to wait and see if these predictions are true. But there are pretty bold claims by many industry leaders that, I think in Google, 25% of the code is written by AI. Similarly, Meta, uh, Zuckerberg says, by 2025, AI can replace mid-level coders. Yeah. Similar predictions also made by Indian industry leaders. So we have to wait and see. But this is from the perspective of industry leaders, and it's for people starting out. I think it might seem gloomy at least for aspiring software engineers. I think The truth is somewhere in the middle. It's probably not so gloomy. But let's look at how software engineers themselves think about the usage of AI. Okay. So instead of just looking from the industry perspective. So this is I present you a summary of a developer survey done by Stack Overflow. Okay, so where around 65,000 developers around the world they took part in the survey, and let me show you some of the results. So here, the question was to developers was, do you use AI in software development process? And as you can see, like the adoption of AI tools in development process is yeah, pretty significant. Like more than 60% are already using. Yeah, so this I think we cannot deny that AI being used uh, pretty significantly in software engineering task. And developers were asked like in which particular uh, workflow, like development workflow, do you typically use AI? And I think around 80%, as you can see, of the people, they say they use AI tools to write code. Yeah, some use for searching for answers and debugging and getting help, also documenting code. But as you can see, the primarily it's about uh, writing code. Okay. Now, do developers trust these systems? And this is where there is a, yeah, the graph is not yeah, as nice as we saw in the last two slides. So here, as you can see, the trust is a bit lacking, right? So highly trust is only 2.7% of all developers, uh, and somewhat trust is 40%. So overall, I think like neutral and somewhat distrust part of and also highly distrust overall. Like more than half of the people, yeah, say either are neutral or distrust this kind of system. So this shows that still a lot of work needs to be done to help developers in various software engineering tasks. Like this kind of data shows this. So the current research also kind of mirrors the overall direction. So it shows uh, the x-axis of this plot shows the years and the number of papers which have which talk about LLMs of code or develop some LLMs for code uh, in each year. As you can see, like the recent trend is some explosive growth of these kind of papers, right? So just in 4 years, there's like a manifold increase in the number of research or the kind of like number of research being done for in particular LLMs for code. And what are the downstream tasks? So for these research papers, so we saw a developer's perspective, like the practitioner's perspective. But what is the researcher's perspective in this regard? So here uh, it shows for those papers that I showed you earlier, how many of like which particular task each of them target. Hmm? So more than 300 papers, like the highest number of papers or research kind of target software development, software testing, and software maintenance. So this forms the bulk, and rest form very little portion of the research being done for software engineering domain in this case. Now, let me give you a very high level and brief introduction on how a typical LLM for SE workflow look like, and then I'll show you one concrete application that to kind of conclude the talk. Right? So the first step, I think, is as with any LLM, you need a lot of data. So the first step is to collect large amount of data. Then you pre-train a model, and in many cases, such LLMs are used for custom tasks. So after the pre-training, as a result, you need to fine-tune these large language models for a particular kind of task, and then the final step is to integrate these LLMs into software engineering workflows. So let me start a bit about collecting data. Where does the data collection for code LLMs come from? So they come primarily from open source code repositories such as GitHub, GitLab. Also, a bit more fine-grained data can come from bug reports, issues, and commits of these repos. So not just code. Uh, Also, documentations, code reviews can be included in this kind of data collection. So, as a concrete example, and the stack dataset is a very popular dataset that uses GitHub archive to extract it. That use the GitHub archive to extract the dataset, and it contains data from more than 350 programming languages, around 6 terabyte of code data. So that's a lot of code data in particular that is collected and used for the next of the LLM. So here comes the next step is pre-training. So in the pre-training phase, what happens is that this collected data is used to train him. So this is a massive code corpora and also natural language. So natural language as in mm, um, uh, uh, documentation of the code. So those are considered natural language. Even question answers websites, they are also used. Okay. So they are collected as we saw, and then they are used to train or pre-train in this case these large language models. So there are certain training objectives that are used for this pre-training. So which are pretty popular. So one is called causal language modeling, one is called mass language modeling, the other is called replace token detection. So here the idea is that you train a model, and then as a simple example in the mass language modeling, what happens is that you try to so you mask one of the let's say word a token it's called, but we can say it's word, and then you try to predict that. So that's how the training works. So this is the objectives in this form of training. Now, in a pre-trained language model, it's so in many cases what happens is that you do not directly use the pre-trained models. You kind of tune it for various tasks. So as a result, you need to refine these pre-trained language models for particular tasks by training it further using specific data sets. So CodeBot is as an example where this language model is then fine-tuned for natural language code search. So one concrete example. Now, the final step after fine-tuning is integration into software engineering workflows. Yeah. So, as an example, GitHub Copilot. I think many of you might have used it. So it has been integrated as a plugin for VS Code and assists developers with writing AI-based code comparisons. Yeah, so you can also use it for NL natural language chats, but the way you integrate in a C workflow is, as an example, is you can create a plugin of a popular IDE, in this case, for example, VS Code or code editor. So, as I said, I want to show you one particular application that I think one of like that I have been part of So in particular, one application. So it's about commit generation. So before I start to talk about the idea about commit generation, let me take a small survey about version control systems. So please scan this. And there are two questions, and just please submit what you feel about those questions so that I know uh, yeah, about the audience a bit, just the background of the audience. So I'll just wait for about a minute. If you have any problems with scanning, you can tell me. Okay, so we have one response already. Okay. Okay. Four response. Okay. Yeah. Yeah, so let me show you how the responses look like. Uh, so I'll stop accepting responses in a minute. Yeah, so currently it's a kind of a 50-50 distribution of 50% are familiar with the version control system. And here it's, yeah, people who are familiar probably, yeah. So uh, they use, so are familiar, they use all the time. Yeah, I don't understand what this means, but anyway, I'll take it this way. Okay, so it's a mixed crowd. Okay, thanks a lot for your quick poll. So just to introduce for people who don't know, so version control systems are kind of a, so when you write some code, you want to preserve the change that you make. Okay, and version control system helps in preserving a particular state of the code. So you can, a very simple example I can think of is, let's say you are using Word documents, and if you use Google Docs, you can go through the history of edits that you can, and you can revert back to a history of a particular Google Doc edit that you made. So if you, so that's a one concrete example. But in code also, if you have something similar, uh, but it's not, like, it's an analogy I tried to use, but it's not exactly the same. And version control system uh, kind of makes, gives you that power, let's say. So in current modern software workflow, version control systems are widely used. And as I was saying, one particular action in version control system is called commit. So commits capture a snapshot of changes that you made to the code base in particular. And commit messages are typically written in a natural language, and they convey the developer's intentions. And primarily, commit messages are for meant for communication with other developers. Okay, so commit messages are, so if you don't use even a version control system, just to give you a summary, that let's say you make some code change, and then let's say you want to preserve that state of the preserve a snapshot of the change. What you can do is that you can commit that snapshot, and you want to write some natural language, like an English description of that snapshot, saying what that change is about. So this is what commit message will look like. So as a very simple example, let me show you this commit message. So this is a commit taken from a very popular repo called HTTP. HTTPD. So it's a very well-known repo for, and this commit is from a guy called Victor, who is a developer in this code base. And yeah, here it just says Greg was right, I was wrong, we don't need this anymore. So yeah, some personal. So as you can see, this message is very informal, right? And it's self-reflective and lacks clear technical explanations, right? Of what the changes are. So there is some code involved here, but the description, like the commit message here, it doesn't really convey what the change is about. Okay? So it also kind of references internal team dynamics between Victor and Greg in this case, and also personal circumstances rather than providing an objective summary. So it's a, yeah, it's a it should as a so what is recommended, that instead of having this kind of informal uh, commit message, it is recommended to have a bit more mm, formal uh, description of what the code change is about. Okay. So people realize this. So there was lot of these kind of commits. So people realize this, and as a result, there is a new kind of specification, which is known as conventional commit specification. So I will refer to this as CCS from now on. So the conventional commit specifications, it provides a simple, standardized way to structure commit messages, and they are project agnostic format, and the format makes commits more readable, and also like commit messages in particular, and also machine interpretable. So here is a simple uh, format of conventional commit specification. So here, as you can see in the previous example, there was no like fixed format, right? So it's just a blob of text kind of. So just a paragraph. But the conventional specifications, they mandates a format that you have to write first the type of a commit. Okay, so what is the code change about? So this is what you write first, and then it's an optional scope you write, and then with a after a colon you write the description, like a single line, natural language English, as an example, description that kind of describes what the code change is about. And the specifications mandates that you must have at least these two: the type and the description. Okay, so let me show you an example. So this is from a commit. This is a message taken from a commit called like from a project called Angular, and the particular commit I'm referring to is the has 3839 CFP. Doesn't matter. So this doesn't really matter. So what this commit is about? So this follows this conventional commit specification. And so as you can see, we have a type here. Okay, so this is uh, called type because this shows what is the type of code change. So probably this code change that is part of this commit fixes some bug, or has some fixes some issue, something like that. So this is why there is a type. The type of the commit is called fix. And as I was saying, that after a colon you have to have a description. So in this case it says router components never inherit router outlet environment injector. Yeah, again, we don't really need to know what this is about, just to show you a real world example of a such a commit. And this is scope, this option which is optional, followed by this is the body, and finally it's followed by the footer. So this is how the structure of a conventional commit look like. So the body kind of provides a bit more description about uh, this particular code change. Okay. So overall, this is how the specifications mandates it. Okay. Now, this work that I'm going to present briefly is about so it's about taking a regular commit that I showed you earlier, and that does not follow any specification, and it is about converting it to a commit following a conventional commit specification. So this is uh, the current work about. Okay. So just to before I go into how it is implemented, a sneak peek of how our approach would output. So given this code change, what our tool recommends is that instead of writing this kind of informal message, it should have been something like a chore, remove http.exp from dist clean target. So this kind of this is the description that uh, describes the code change, right? And this is the type of the um, of the commit, like code change basically. So type means developers typically use this type to signify routine maintenance. So this is probably about maintaining the code, right? So instead of this informal, our tool can generate this kind of formatted and commit messages. So let me give you a brief overview. Um, uh, So we start with an unstructured commit. We have an summarizer LLM that summarizes uh, the code of this unstructured commit. Then we combine with the commit message, which is still unstructured. One of the commit message I showed you earlier, and with this we get a commit intent representation, and we use this commit intent representation to two LLMs. So one LLM generates the type, and the other LLM generates the description. So this is, as I was saying, that these type and description are the two primary mandatory features that you must have in a conventional commit specification. So one LLM gives us the type, and the other LLM gives us the description. Okay, so this is a very brief overview of our approach. Let me start by talking about each of these sub parts of the approach. So let me start with the summarizing part.
Dr. Jibesh, I'll just interrupt.
Yes.
So in the previous slide, do you check if the description matches with the type, or is that like part of the process? Like, as in, maybe the type is completely different and the description is completely different.
Yeah, so combined we check, of course, but for evaluation, yeah, uh, when we generate them together, uh, we use so the type and the description, they are not that much related as such in this
I
case.
see. I see. Like, for example, somebody wrote, let's say, cosmetic, and then did this same description as I removed this particular file from this target. If somebody, do we need to check even type and description are in the same bucket?
Yeah, so we yeah, I think they make sense, of course, together. So like, of course, there has to be some semantic similarity between type and description, so that is correct. But in this case, yeah, so in this particular scenario, we don't really use type to predict the description. This is what I was trying to say.
I see. I see.
So
Okay.
we predict type independently based on rest of the commit, and similarly we do.
I see. Yeah.
Okay, yeah, thanks for the nice question. Okay, so any other questions also I can take here? Yes, Sachin.
Can you just go to back, I mean, the previous slide?
Yes.
So here are we, like the summarizer LLM is actually going through the code or just the, I mean, it's also looking at the unstructured commit message?
Yeah, so I'll just come to that because I plan to explain what this does. Okay.
Okay.
Yeah. Good. Then I'll move forward. So the first step is uh, is to find a file level difference. So we use the default algorithm of Git to find the file level difference. So in this case, it is just the code. Okay, so the difference between the code, and then we use. So instead of directly using the code, what we do is that we use the summary of the code. So to answer your question, we take the unstructured commit, we find the diff, so that is the code changes most typically. So we don't take the commit message in here, okay, and then we give it to the summarizer LLM, and we get a summary of the change. So instead of directly using code, we use a natural language summary of the code. So this is what we do in this case. Okay. Hope that answers the questions. Or yeah, Sachin, please.
Yes.
Oh, it answers the question. Sorry, I understood. You have more questions. Good. So, just to give you a peek into the prompt that we use. So, it's a very, just go through quickly. So, you are a code summarizer based on Git diff, and then we give the file, and then we are using, and we give a context to the LLM, and then we give the files here. Okay. And then we give some few short examples of how the summary should look like. Okay, so this is how the diff looks like. Okay. Um and then the output is something like this from the LLM, that file is this, and these are the summary of the changes that are made to the file. So use a another LLM just to get this kind of summary. Okay. The next step is to combine with the commit message. So a commit is made up of a code changes and a message. So as a result, the code changes summary we got from an LLM, and then now we combine it with the message, and this gives us a commit intent representation. And this we use this commit intent representation we use for our next task here. Okay. So as I was saying, we focus on the two mandatory parts of CCS. So the type and the description, and we use one uh, LLM just for the prediction of type, and one LLM just for the prediction of description. Uh, there are certain challenges in, and why we kind of consider this kind of architecture is the conventional commit specifications it recommends but does not really enforce any type except two. So it just says these are the two types you have. Feat usually you use for feature, adding a new feature, and fix you use for fixing some issue or bug or something like that. So there is a long tail distribution of types. So this is a snapshot from our data set. And you can see uh, like there are like this the types that are used by developers is a forms a long tail distribution. And so I don't show all the types. I think I just this plot just shows the top 10 types. Okay. And another challenge is no specific definition. Okay. For of a type. So, as a very simple example, one particular type could mean two different things for two different project. Okay. So yeah, so it's kind of a difficult in that scenario. So these are the two primary challenges. So that's why we wanted to use only one because of this long tail distribution, and also not adhering to a common definition. Yeah. So there are one particular solution that people have tried to come up with is that manual. So since there is no particular definition, so what what do you mean by a type called chore? or a feat, right? So feat is it's present here, but sorry, but docs or refactor, yeah. So these don't really have a universal definition. So as a simple example, this feat even is not universal. Yeah, so it could mean a new feature for a library for external users, but also it could mean a new configuration for development and deployment in an infrastructure project. Yeah. So these are some solution. One solution is that you kind of define it manually. So what you do is that you go over multiple projects and then you, yeah, define each of these type manually, which people have tried to do. Yeah, but as I said, it has some scalability issues, right? So you cannot define all of the types by going through and understanding each of the type. Yeah. So our approach so does not need any manual definitions of type. So that's one thing, and also meaning of the type. So our insight is that for a particular code base, one, if I select a type, the type is the meaning of that type is consistent at least for that code base. So it doesn't have to be project agnostic, but it can be just project specific, right? So this is what we do. So what we do is that we perform a project specific um, uh, training. So for our LLM type, we take the types and rest of the commit, and and we fine tune an LLM to get a our uh, LLM type in this case. And for description also, so description in particular does not have this kind of semantic problem that I talked about the type, but description, one of the big problem about description is that the length, right? Yeah. So some as I said, like the CCS, they do not really mandates the writing the body, so it just mandates the description. So many of the times people just do not write the body of a commit message. So in this case, what we do is we try to predict the description of the commit by only selecting those commits that has body, and then tune a model based on that. Okay. At this point, we don't have this data available, so this is still a bit of work in progress. Okay, so at this point, no, but once we are done with with this particular data set, we plan to, of course, release to the public. Okay, so let me show you some results. This is about checking the correct adoption rate and find the effectiveness of our approach in generating the type and description of a conventional commit. So as I was saying in the beginning, this commit specification is pretty new, and we want to check how the commit specifications are being adopted by different projects. So there are so our benchmark, we collected around top 500 repositories from GitHub based on their stars from 13 programming languages, and our data set contains around 6,500 open source repositories with approx 21 million commits. So just to give you small statistics, we found that of these 6,500 repo, yeah, only about 1,247 repo has at least 70% compliance. So which means that at least 70% of the commits in these repos at least comply to conventional commits or follow this specification. And from the commits perspective, around 24% of the 21 million commits, they follow the specification. Okay. And as I was saying earlier, that the types form a long tail distribution which limits, like, which is a bit of challenging to predict a single type. Developers in overall these 5 million commits came up with 215,000 distinct types. So you can imagine, to predict this kind of it's kind of a bit of challenging. Just to show you the year-wise adoption of conventional commits, so this shows the compliance rate across repo. As you can see, the compliance rate is slowly but steadily increasing across repo from the perspective of project level adoption. So that is about from the perspective of programming languages, TypeScript, Go, Rust. So uh, yeah, uh, the so bit less traditional, I would say. uh, where there are more new developers, it seems, at least from my perspective. The CCS compliance rate is higher compared to C is still up there, but Java, C Sharp, Swift, even Python, yeah, they have less adoption. Yes. Now, for generating the types, we evaluated on 5 popular GitHub repo sampled from our datasets. As I was saying, we learn project-specific types and checked. So we have 3 configuration for generating the types. So one is the default, that is learned from the commits taken from the same repo, right? So to predict the correct type. One is manual, so where a manual definition is provided as part of the learning. Okay, so that is during the tuning of the model, we we provide what each type actually mean. So what does fit mean? Okay, so that is, this definitions has been manually created for some top 10 of such types, and they are provided as part of the training. And finally, global. So global as in where we learn the commit type by sampling across. So we train a model where we sample across all commits, and then and then where the task is to predict the correct type, right? And then we evaluate on uh, each of these projects. So these are the 3 configurations, and here is the results of these 3 configurations. So one is so the middle is our default approach, where we use the project specific training data. And on the first column you see the name of the projects, the number of stars, and this tick and cross, they show that does the project actually uh, have any CCS guidelines. So what we found, actually, just to some brief comment about this, is that many of these projects, although adopt uh, conventional commit specifications, they do not themselves have any agreed upon type definition. So which was a bit of strain, right? So as you can see, Deno is a popular project which has more than 100, around 1 lakh, I think, stars. But it doesn't have in the repo for the developers mentioned what each of these types that they have, like fix, shore, feed, refactor, what they even mean. So as a new developer trying to uh, contribute to these projects, it's kind of difficult to create a type uh, for them. And this is where we see our approach kind of sign, because our approach can see and learn from the past history of past commits and types, and can help developers in selecting a correct type. So as you can see, we also found that a global model, yeah, it's kind of doesn't work that well. Yeah, a manual, of course, works pretty good, but it's not does not. We still outperform the manual approach, where each of these types, that is fixed, score, fit, the definition of them are also given as hints to the language model. Okay, so this is about predicting the type. Mm, for generating the description, we use a metric called blue score, where it is generally traditionally used in natural language processing for evaluating the quality of generated text by a model, and it compares to the reference. So higher scores signify closer generated text. So for this particular task, we you compared our work of generating the description to two other models. So one is GPT-4o and the other is Gemini. So for this task, what you did is that for these two models, we gave some few short prompts, and then asked them to generate the description, because we could not tune them these models ourselves. And then for our case, this LLM description, what we did is that we sampled around 2000 CCS compliant commits that contains a body, and then we train our model with that. Yeah. So we find that at a significant smaller model. So one thing I should mention, for all of these LLMs that we use, our model is based on Llama 7 million. So for description also, the LLM is very small compared to these large models that are used in production or industry. So we find that a significantly smaller model, fine-tuned for a very, yeah, purposely built or purposely fine-tuned for generating description, yeah, outperforms both the general purpose models. Okay. To give a summary, so adoption of CCS is rapidly growing. I think if you use version control systems, I would recommend to also adopt conventional commits for your commits messages. We found that developers find it difficult to assign the correct type to a commit, because in many cases there is no universally agreed upon definition of the types, and a global definition is difficult to assign, because the semantics of a particular type changes might change across projects. And we present one approach that automatically generates type by learning from project history and description from general commit body. So that's all from my side, and thank you very much for listening. I'd be happy to take any further questions.